Welcome to Square Ek Patshala. Today, we are mastering electrostatic potential and capacitance. Be sure to join our channel as we break down these derivations step by step. Look at this diagram comparing a water tank to an electrical circuit. Just as a tank builds up fluid pressure to release it all at once, a capacitor stores electrical charge to dump it in a sudden, concentrated burst, exactly how a camera flash works. To understand how it stores that energy, we have to look at this glowing heat map. This represents electric potential. Think of it as the invisible electrical pressure required to push a charge through a field. Potential is not a force itself. It is a direct measurement of the external work you have to do against an electric field to move a unit positive charge from infinity into a specific position. This diagram shows a test charge, Q0, starting at infinity and moving toward a central positive point charge along a defined distance, r. Notice these opposing vectors. The electric field naturally pushes the test charge outward, but our external work pushes it inward. Because these forces act in exact opposite directions, the angle between them is 180 degrees. The cosine of 180 is -1, which introduces a negative sign into our work equation. To find the total work done, we integrate this force from infinity to our actual distance, r. The integral of x to the power of -2 becomes -1 over x. Those negative signs cancel out, giving us our final mathematical relationship. Electric potential drops off inversely with distance. This 1 over r relationship forms the mathematical baseline that dictates how energy behaves in every complex electrical configuration we build next. Here is an electric dipole, a negative and positive charge separated by a distance of 2L. Our objective is to calculate the net potential at this target point, P, located straight down the axial line. Because potential is a scalar quantity, we do not need to calculate vector components. We simply take the baseline formula for the positive charge and add it algebraically to the negative charge. After finding the common denominator, the distance now drops off much faster, yielding a new relationship of 1 over r squared. Now, look what happens if we move our target point P to the equatorial bisector. The physical distances to the positive and negative charges are perfectly symmetrical. The opposing potentials cancel each other out entirely, dropping the net potential to absolute zero. When calculating the potential energy of a multi-charge system, the signs of your charges tell you the physical reality. If you bring two like charges together, they repel. You have to force them together, so the potential energy is positive. If you bring opposite charges together, they attract, releasing energy, making the system's potential energy negative. Because potential lacks directional vectors, system stability is dictated purely by the algebraic signs of these interacting charges. This visual maps out equipotential surfaces, areas in space where every single point shares the exact same electric potential. You see concentric shells for isolated point charges, parallel planes for uniform fields, and distinct contours for dipoles. Notice how none of these lines ever cross. If two equipotential surfaces were to intersect, that single physical point would have two different voltage values simultaneously. That is mathematically impossible. Mapping these surfaces provides a direct visual cheat sheet for field strength. Where the surface lines are packed tightly together, you know intrinsically that the local electric field is strong. Let's see how a capacitor increases its own storage capacity without changing its physical footprint. We start with plate A, loaded with a positive charge. When we bring an uncharged plate B nearby, induction pulls negative charges to its inner face. By grounding the outside of plate B, the free positive charges drain into the earth. The remaining negative charge severely drags down the total potential of plate A. Because capacitance is charge divided by potential, lowering the potential increases the capacitance in direct proportion. For parallel plates in a vacuum, we convert the electric field to potential by multiplying by distance, yielding a final capacitance of epsilon0 times area divided by distance. Look at that final formula. Capacitance is a purely architectural property. It is determined exclusively by plate area and separation distance, entirely immune to the amount of charge applied to the system. This diagram outlines the most complex derivation you'll face, calculating capacitance across a split medium. We insert a partial dielectric slab of thickness T between the plates, leaving an air gap with a thickness of D minus T. To find the new capacitance, how do we write the equation for the total potential across these two distinct zones? The total potential is simply the sum of the air field times its distance, plus the dielectric field times its distance. Because the dielectric slab shrinks the internal electric field by its constant factor, K, we substitute E0 over K into the slab's portion. We pull out the common E0 factor. When we plug this reduced potential back into our primary equation, the charges cancel out. Decreasing the overall potential strictly drives the capacitance up, locking in our final master formula. Inserting any dielectric material structurally chokes the internal electric field. This effectively acts as a mechanical multiplier, increasing the system's total storage capacity without expanding its size. This matrix contrasts our core models. For a standard point charge, potential drops off at a rate of 1 over r. But for a dipole, the opposing charges cause the potential to drop off much faster, at 1 over r squared. Lock in these definitions. 1 farad is the capacitance achieved when 1 coulomb of charge raises a conductor's potential by 1 volt. And remember the trick question: doubling the charge on a capacitor does absolutely nothing to its capacitance. Mastering these derivations allows you to calculate exactly how much charge a system will hold and how much work is required to assemble it. Keep practicing these steps, and make sure to subscribe to Square Ek Pathshala for more straightforward masterclasses. See you in the next lesson.